Okay, so thanks to Till's wonderful introduction, I don't need to waste a lot of time on this slide. What I do want to call your attention to is the fact that the research group Epistemology and Ethics of Machine Learning is hiring. So we're hiring between 1 and 2 PhD students and between 0 and 1 postdocs. And if you want the links to the ads, please go to my website, which is myname.com. Okay, so morals and methodology. I think we're all more or less accustomed to the idea that methodological questions in science depend on ethical questions. So for example, if an experiment is unethical, it shouldn't be performed. If an algorithm is unjust, it shouldn't be implemented. Now, from this perspective, I think the normal one, the picture I have in my mind anyway, is that researchers advance methods, they come up with new tools, new machines, and ethicists have to rush to install new guardrails to keep them from going off the track. So when people were racing around in like machines like this, the ethicists had to install these kinds of guardrails, stacks of hay. Then when the techniques advance, they have these kinds of cars, you need to come up with something new, like, well, what do we do? Maybe we stack tires at the side of the road so that to minimize the crashes. And now when you have these like extremely sophisticated looking cars, like, well, the question is, what do we do next, right? And I don't want to minimize the importance of installing guardrails. Guardrails are very important. But this kind of reactive picture is a little sad to me because well, ethical questions also depend on methodological ones, right? So the idea here is that methodological progress shouldn't just lead to like a frantic rush to kind of constrain what machine learning people in artificial intelligence can do, but it should also, methodological progress should lead to moral progress. So for example, I guess we're familiar with the idea that randomized controlled trials in medicine and social science raise a variety of ethical issues, but they're justified by their epistemic advantages, especially with regards to causal inference. But as techniques for causal inference from observational data progress, there's pressure to reconsider the ethics of randomized controlled trials. I don't think we're there yet, but it's not so far-fetched to think that the kinds of techniques that are being developed for causal inference from observational data eventually get so good that there's pressure from randomized controlled trials to justify the use of randomization, experimental method, especially when it comes to human subjects. Like, why? If it looks like the techniques from observational data are kind of catching up in terms of epistemic advantages. So the basic idea is that methodological progress should lead to moral progress. So on the left, the picture I have in my mind, of course, is like on the left, we have William Harvey doing some unspeakable thing to a dog, to a poor dog. And on the right, we have a cute kitty cat receiving a entirely not invasive ultrasound, right? There's no need to cut up live animals in order to like learn things about the circulation of the blood anymore. Sorry, I have to rearrange these little windows. There we go. So as Till said, the goal of the ethics and epistemology research group is to approach the issue from both sides. So how do methodological constraints express themselves as ethical constraints, and how should ethical constraints be expressed in methodology? So up until now, like during my dissertation and during my postdoc, I've mostly been focused on methodological issues. And I like to call this learning-theoretic epistemology. But you can also think of this as an ethics of inquiry. So in learning-theoretic epistemology, we're interested in epistemic justification. What is epistemic justification? Well, if you're faced with some kind of scientific problem, epistemic justification consists in solving the problem in the best sense in which it can be solved. And a learning-theoretic analysis of the problem, well, basically there's 3 parts to it. You have to first specify the problem context. What is the question we're trying to answer? And what relevant information can we hope to acquire as inquiry continues? And then you have to analyze the inherent difficulty of the problem. Given the kind of information that we have available, what's the best sense in which our problem can be solved? And once you have a sense of the inherent difficulty of the problem, you can identify the best methods for solving the problem. None of this should seem groundbreaking from a computer science perspective. Tactically, the technical apparatus uses topology. And why topology? Well, topology is the thing you use to analyze the inherent difficulty of a problem. Now, I don't expect you to get the details, but just to get a sense for why topology. So in the statistical setting, we have some set of possibilities, possible models, possible explanations for the phenomena that we're investigating. And then we have a question, which just partitions those that set of models into a countable set of answers. Now, topology is a kind of qualitative geometry, which abstracts from metrics of distance. What do I mean by qualitative geometry? So focus on the point here on the lollipop where the handle meets the candy, and assign that arbitrarily. Is that point part of the handle or the candy? Assign it arbitrarily to the handle. So that a point is a limit point of a region. Here I have in mind the candy region. If every neighborhood of that point contains some point of that region. So here in this animation, every neighborhood of the point where the handle meets the candy catches some part of the candy. And that relationship between the handle and the candy is invariant over various kinds of transformations. So if we mapped the set of the candy, the lollipop, to this kind of shape that we have in the middle, or to the heart shape on the right, the qualitative relationships between the handle and the candy don't change. There are still points in the candy zone that approximate or get arbitrarily close to the point on the handle. That's why sometimes people say topology is the study of transformations that don't involve gluing or cutting. So why gluing and cutting? Well, cutting, it's because it separates, it takes away limit points. Things that were limit points are no longer limit points because regions that were not separated become separated. And gluing is because it introduces limit points. So things that were separated become unseparated. So topology is the study of transformations that aren't like that preserve relations of qualitative nearness or arbitrary closeness. And okay, so two regions are well separated if no point of one region is the limit point of the other one. So for example, the candy and the handle are not well separated because there's a handle point that's a limit point of the candy region. Now, what does this have to do with epistemology? If we interpret the points as epistemic possibilities, like models or relevant explanations that are competing to be the explanation of some phenomenon, and we interpret the neighborhoods as information states that narrow down the set of possibilities, then topology captures how well hypotheses are separated by information. It captures how well the information that we could get resolves the possibilities that we're interested in. And so it captures the structure of empirical underdetermination. And what we wanted to know was how difficult our problem was, because how difficult our problem was sets the standard, the kind of ethical standard for what it means to solve it well. And so why topology? Well, the inherent difficulty of our problem is exactly how underdetermined the question is by information. So topology is exactly the right kind of thing to study empirical underdetermination and to tell you how hard a problem is. Okay, so in these pictures, we're imagining something. We're imagining that we get information states, these kinds of like circles that narrow down the set of possibilities. In statistics, everyone knows that you never really get that kind of information. Everyone knows that any statistical model is typically logically compatible with whatever kind of data you get, although some possibilities are more likely and some are less. They're all logically compatible. So this picture here is a kind of myth, right? Because you never get information refuting possibilities. But that's okay. So let's say that a hypothesis, by a hypothesis, I just mean a set of models, is alpha refutable if and only if there exists a consistent hypothesis test of H with a significance level alpha at every sample size. And we're going to say that a statistical hypothesis is refutable if it has such a test for every alpha greater than 0. You can shrink down alpha arbitrarily small, but never perfectly. Here is what I just said in math, if you prefer. So a hypothesis is alpha refutable if there's a sequence of tests, one for every sample size, such that the power of the test converges to 1 in all the possibilities outside of H, and the chance of a type 1 error stays bounded for all the possibilities inside. Okay, so here's a theorem from a paper, a collaboration with Kevin Kelly in 2017. So under a weak assumption about the set of possibilities, the following are equivalent. A hypothesis is alpha refutable for some alpha. It's refutable in the sense that like you can drive alpha arbitrarily small. It's monotonically refutable. That just means you can drive alpha down and you can send the power up in a nice way. And it's closed in the weak topology on W. So that is the first of a kind of a series of results that relate topological complexity. Is it open? Is it closed? Is it a union of closed? Is it a union of locally closed? Topological complexity to methodological accessibility. So what you can do is, just starting with this building block of refutability, you can build weaker and weaker notions of methodological accessibility that correspond to greater topological complexity. So for example, I talked to you about closed, but in statistics, the only result that I'm familiar with in statistics that's kind of similar to our work here is about limiting decidability. So a hypothesis is decidable in the limit if there exists a series of tests such that they converge in chance to believing not H if H is false, and they converge in chance to believing H if H is true. But there's no guarantees for what it does in the short run. It can do wild things in the long run as long as it converges it can do wild things in the short run as long as it converges as sample sizes increase in the right kind of way. And say that a hypothesis is limiting clopen if both it and its complement are countable unions of refutable hypotheses or closed sets. Those are equivalent. And so Dembo and Perez have a paper in 1994 in the Annals of Statistics, a topological criterion for hypothesis testing that basically characterizes decidability in the limit. It says H is decidable in the limit if and only if it's limiting clopen. But they don't build it out of, simpler notions of accessibility. They don't build this whole hierarchy. They're kind of just focused on one level in the hierarchy, but an important one that we will see comes up later. Okay, so with these topological notions, we can give a kind of explication of a notion of simplicity, and this notion of simplicity is inspired by a notion that Karl Popper proposes in his famous book, A Logic of Scientific Discovery. So say that two disjoint sets of models, meaning like genuinely competing explanations for some phenomenon, say that A is as simple as B if all testable consequences of B are testable consequences of A. Equivalently, all refutable consequences of B are refutable consequences of A. That's equivalent to now a topological expression. The closure of A is a subset of the closure of B, or equivalently, A is a subset of the closure of B. So this is a topological expression of a notion of simplicity proposed by Karl Popper in that famous book, where incidentally, he also proposes a notion of VC dimension. So he proposes many different notions of simplicity. One of them is this one, and another one is very closely related, except for a flip of quantifiers, to what we know now as VC dimension. So recall, a question is we just partition the set of possibilities into a countable set of answers. And I just want to introduce some notation. So if we have this particular model, we say Q sub M is the answer true at M. Okay, so a solution to a problem is just something that converges to the true answer, whatever it is. converges in chance. So for all the models in our set of possible explanations or set of models on the table, the probability there in that model that your method converges to the true answer at m converges to 1 as n gets large. And we say that the question is solvable if and only if it has a solution. So if it has one of these methods. Okay, but a solution, again, it's just this long run, it's extremely long run idea. And that's very weak, right? So we want to strengthen the notion of progress, because what? Convergence in the limit, this is like an old critique of learning theory, is that convergence in the limit is compatible with any old kind of behavior in the short run. So for 1,000 years, you can do something like, you can throw dice or spin a wheel to say what answer to output. As long as you switch to a consistent method, that method is consistent. So we want some kind of stronger notion of success other than convergence in the limit. And so say that a solution is progressive if for any 2 sample sizes, the probability of getting the right answer at the smaller sample size, the probability of getting the right answer at the larger sample size is no smaller than at the sample size. Basically, this is saying collecting a larger sample is a good idea because it means that the chance that you'll get the right answer is improving. And what is a failure of progressiveness? Well, that would mean that sometimes it's a bad idea to collect more data because the chance that you'll get the right answer at the larger sample size will be smaller. So that doesn't sound right? Unfortunately, although everyone kind of, I think, wants or expects that statistical methods have this property, that collecting larger samples is a good idea, they don't. And sometimes it's impossible to satisfy this, but we can sort of approximate it. So it's an ideal that we'd like to approximate. So say that a solution to a problem is alpha progressive if collecting a larger sample never sets you back very far. So at a larger sample size, if you just add alpha, it will be the chance of getting the right answer will be better than before. So it's easier to explain with a picture. On the left, so what are we graphing here? We're on the x-axis, we have like sample sizes, and on the y-axis, we're graphing the probability of getting the right answer. On the left, we see that the dips are much smaller than they are on the right. And so the picture on the right is not alpha progressive because there are sample sizes, there are pairs of sample sizes, such that at the larger one, your chance of getting the right answer is significantly lower. Yeah. So like failures of progressiveness are kind of epistemically perverse. They're essentially designed in dispositions to fail to replicate. But failing to replicate false things is good. Failing to replicate true things is bad. So failures of progressiveness are designed in dispositions to fail to replicate true findings. So say that a problem is progressively solvable if it has an alpha progressive solution for all alpha, meaning you can't drive the dips to 0, but you can make them arbitrarily small. So as I said, surprisingly, many standard statistical methods are not even approximately progressive. So here, I know of one paper, at least in statistics, that investigates this. It's Chernik and Liu's paper, The Sawtooth Behavior of Power. And here what we're looking at is you pick some particular parameter, and now you're looking at the power as sample sizes increase. And you can see that there are pairs of sample sizes, such that at the larger one, your power is significantly worse. And that's strange and perverse behavior that you would like to avoid. Can you guys see my pointer? So you see what I'm pointing at? Okay.
Yes.
Great. So what does this mean? So performing a replication study with a larger sample and a lower chance of replicating successfully, that's not just epistemically bad, it's unethical if you really imagine doing such a thing. Say it's a drug trial, and what you're saying is, I propose to do a replication at a larger sample size with a vaccine or something like that. We collect more people who we're going to vaccinate, but the probability that I figure out whether the vaccine is better than placebo is worse at the larger sample size. That's just wrong. It's not just wrong, it's probably unethical, because why would you expose people to possible side effects, etc., for no epistemic gain, right? Okay, so here's a theorem. If the answers to a question can be enumerated in agreement with simplicity, then it's progressively solvable. What do I mean by enumerated in agreement with simplicity? I mean, there is an enumeration of the answers such that you never have to put something strictly simpler after something more complex. So that's nice, I think. And another neat result, I think, is that every alpha progressive solution to a problem has to satisfy a version of Occam's alpha razor. What is Occam's alpha razor? So here's the definition. So a solution satisfies an alpha razor if the probability in every world, the probability in every possibility in every model, the probability of outputting an answer more complex than the true one is bounded. So if you're going to make a mistake, it's on the side of simplicity. You're always this is a version of Occam's razor that says always err on the side of simplicity. And if the probability of saying an answer more complex than the true answer is smaller than alpha for every such answer. So this is a kind of non-circular epistemic justification of Occam's razor in statistical practice, because it doesn't assume that the answer is true or probably true. It doesn't impose any prior probabilities or anything like that. It's just purely universal statement. Every alpha progressive solution to a question satisfies Occam's alpha razor. What is Occam's alpha razor? Well, in every possibility, the probability that you output at every sample size, the probability that you output an answer more complex than the true one is bounded by alpha. It's bounded to be small. Okay, that's pure theory. And what can we do with these kinds of results in terms of applications? So when I was working on my dissertation, the application that I had in mind was, since I'm from CMU and we love causal inference there, is causal discovery from observational data. So these kinds of causal discovery, causal searches are strongly guided by simplicity. And how does this generally go? You prefer sparser graphs with fewer causes, simpler graphs, and you introduce edges, you introduce more complicated graphs with more causal connections, only when sharply testable conditional independencies are statistically rejected. So when you reject certain kinds of conditional independencies, you are induced to introduce edges to explain these lacks of conditional independence, and that forces you up the ladder of complexity of the graph. Okay, so Spirides et al., our colleagues at CMU in 2002, they proved that under a bunch of assumptions that if you don't know what they mean, it's not that important, causal Markov, causal faithfulness, causal sufficiency, when these conditions are satisfied and relevant tests of conditional independence exist, it's possible to converge pointwise to the Markov equivalence class of the DAG generating the data. So pointwise just means that you get there eventually. You can't specify a priori a sample size by which the output of the method is reliable or probably reliable. You just know that it will get there eventually, but you cannot, like in statistical learning theory, specify a priori a sample size by which you know that the outputs of the method are probably reliable. Furthermore, okay, so I mean, pointwise consistency isn't nothing, but the problem is that there are infinitely many other pointwise consistent algorithms, other than the ones recommended by our friends at CMU, that would give different results on finite samples. And many of these, presumably infinitely many, would reverse the preference for sparsity. So what justifies the usual methods, right? So what I'm saying is, suppose you had a consistent method in the sense of in a pointwise consistent method for learning the Markov equivalence class of the true DAG. Pointwise consistency is very weak. So if you wanted another pointwise consistent method, you could, for the first 1,000 years, look at the entrails of animals to figure out what to say, what are the causal explanations, and then switch to PC or FCI or one of these things that they recommend at CMU, and then you would still have a consistent method. Excuse me, I'm getting a little sore throat. So Spirides et al., they know about this, and they kind of complain about it in the book. Most of the algorithms we have described require hypothesis tests, but the parameters of the test cannot be given their ordinary significance. And neither the significance level nor the power of the test measures anything interesting about the search. So basically the usual things in frequency statistics that give you some kind of short-run guarantees, power, significance, none of them have their usual interpretation. And moreover, we know that uniform consistency is impossible to achieve under the usual assumptions. There's a nice paper by Robbins, Shyness, Spirides, and Wasserman. So the picture I have in my head is something like this. Everyone wants uniform consistency. What does uniform consistency mean? That means I can specify a priori a sample size by which the output of the method is probably correct. But what you really get is pointwise consistency, no such guarantees. You just know that it'll get there eventually. And in between, there's kind of nothing. There's just these tumbleweeds and cacti, right? So my proposal is to stick this here between them, progressive methods. So progressiveness is stronger than pointwise consistency, but weaker than uniform consistency, and it's actually achievable. Of course, it would be, if we could have uniform consistency, we should. But since we can't, we should do better than pointwise, and we should try to be progressive. And so here's a theorem. So when all the usual conditions are satisfied and the relevant tests of conditional independence exist, it's possible to converge alpha progressively to the Markov equivalence class with the DAG generating the data. Oh my God, it's awful. For all alpha greater than 0. So you can, and well, the punchline, I should say the punchline. And every alpha progressive solution to this causal inference problem must prefer sparse DAGs. And that'll give us a new interpretation of the parameters because you have to manage the parameters in a certain kind of way. But that justifies the usual methods because you have to prefer the sparse DAGs because otherwise you don't get progressive conversion. Okay, but there are many, many questions that present themselves after you have a result like this. So for me, I started getting puzzled about when do we know that the relevant tests of conditional independence exist? I mean, this is just saying if they exist, then you can do this kind of thing. But in general, we don't have any answer to when they exist. In fact, Shaw and Peters, colleagues, I think Peters used to be here in Tübingen. I'm not sure about Shaw. Show that in general, conditional independence is not a testable hypothesis. And they have this paper, The Hardness of Conditional Independence Testing. And it's a very cute argument that I think is easy to explain and easy to illustrate topologically. So the point is conditional independence is not closed in the weak topology. In other words, conditional independence can approximate conditional dependence arbitrarily well. We're sort of, at least I was used to the idea that you can, since independence is this very sharp kind of thing, you can approximate it with dependence because dependence has a lot of slack. The interesting thing is that you can do the other way, that you can approximate dependence with independence. And so I'll show you how. So let x and y be some continuous random variables that are dependent given z. Now snip off the tail of the binary expansion of z at some point, n1. Snip it off. Now copy x and paste it in. That creates a new random variable, z1. Now y is independent of x given z1. Why? Well, z in the tail of z, rather the tail of z1, contains all the information about x. So given z1, y couldn't possibly tell you anything about x that z1 didn't already tell you about x. And it doesn't matter where you do the surgery. You could have done it at n2, you could have done it at n3. So here's the picture. Depending on where you do this surgery, the probability that the difference between xyz and xyzn for any n is large is bounded, obviously, because they get very close, because you're doing the surgery way down the binary expansion of z. So in the Euclidean metric, these things are always very close to each other. And so as you do the surgery further and further down, you get that the xyzn are converging in probability, and therefore in the weak topology to xyz. So what does that mean? That means that XYZ is a limit point that's missing from the hypothesis of conditional independence, which means that the hypothesis of conditional independence is not closed because it's missing a limit point. That means it's not testable. So that's really sad. So we were hoping conditional independence lived here in this level of the hierarchy, but Shaw and Peters prove that it doesn't. So there's another paper. For some reason, I'm saying it's 2017, but the right citation is 2012, saying that, okay, yeah, you can't make a hypothesis tests for conditional independence, not in general, but you can decide it in the limit. You can converge to the right answer as you get as sample sizes increase. You just can't bound in the short run any chances of error. I actually think that that's not true, and there's a mistake in that paper. I recognize the mistake because I made the same mistake in my dissertation. So it's a mistake that's close to my heart. And I actually think that the situation is much worse. Conditional independence is like really hard, at least in general, to learn about. But here's my question, and this is now a speculation. Is this an artifact of our definition of conditional independence? So we're used to working with real continuous random variables, and the definition of conditional independence is very fiddly, because it says that x and y are independent given z if perfect information about z renders y uninformative about x, meaning like if you specify the value of z exactly, sort of. That's not exactly technically right, but yeah. But we never have perfect information, z information. I mean, anytime we record something in our computer, it's going to be discretized. It's not going to be infinitely precise. Moreover, the interventions that we're interested in performing in the world are also not infinitely precise. We never set a continuous, we can never do an intervention that sets a continuous variable to some precise real number value. That's just insane. So given that the interventions we are considering are only epsilon precise, is there a fuzzy version of independence, conditional delta independence, that's sufficient for predicting the results of interventions? So in a way that like this could turn our weakness into a strength. Our weakness in intervening precisely might mean that we only need approximate conditional independence information to predict the effect of the fuzzy intervention. And so all of this like difficulty around conditional independence might just be an artifact of the kind of machinery we're used to using, which is convenient for doing analysis, but makes epistemology look impossible. And that's a typical thing. Things that make the math easy make the epistemology impossible. And that's kind of all over the place. Okay, so all of the stuff that I said was very much in the domain of constraint-based search. Everything you can learn about causation is somehow embedded in relations of conditional independence. But since then, our colleagues here and elsewhere have developed a lot of interesting new algorithms that don't depend essentially on conditional independence information. For example, the famous Lingham model. They show that when noise terms are independent and non-Gaussian, and functional relations are linear and acyclic, and there are no unobserved confounders, it's possible to converge pointwise, again, to the DAG, not just some equivalence class, but to the DAG generating the data. And that was kind of amazing when we at CMU learned about it. But again, pointwise convergence is compatible with all kinds of short-run behavior, and causal conclusions may flip arbitrarily often as data accumulates. So here's a paper from my advisor, my PhD advisor, Kevin Kelly, and Connor Mayo Wilson, one of his students at the time, that shows that you can get the standard methods to become very convinced that X causes Y, and then become very convinced that Y causes X at larger samples, and then become very convinced that X causes Y. And in principle, you can get them to do this arbitrarily often. So here on the right, we have a graph of FCI doing these kinds of reversals. And you see at this sample size here, if you ran FCI and published your results, you're essentially publishing the result of a coin flip. Probably you shouldn't do things like that, especially if you can avoid it. If it's not avoidable, okay, but if you can avoid it, then you should. So here's a result that we recently, well, it's forthcoming in a paper at NeurIPS with collaborator Connor. Under the Lingam assumptions, there exists alpha progressive methods for learning causal orientation for every alpha, and these can be kind of combined together to create methods that don't flip. These methods will never, with high probability, these methods have bounds. Sorry, what I mean is, if these methods are unsure about whether x causes y or y causes x, they will suspend judgment, and they will only make a decision when there's a bound on error, a solid bound on error. So it'll, if it causes x, if x causes y, it'll only, the probability that it gets the orientation wrong is low, and it converges in the limit as well. So it's strictly better than pointwise convergence. And why? I mean, I can't explain to you exactly why, but it's because topologically, although the possibility in which there's no causal connection between x and y is a limit point of both of these possibilities, the left x causes y and the y causes x possibility, they themselves are topologically separated from each other. And if you want a neat proof, see my paper with Connor. It's pretty simple, in my opinion. Of course, okay, all of this depends on, there being no unobserved confounders, and everyone knows that in real science, unobserved confounders are the things that we're worried about. So here's an important question. So how far can this be extended to cases when there are unobserved and unobservable latent variables or confounders? That question is particularly important, I think, in algorithmic fairness. Okay, so transitioning now to the subject of algorithmic fairness. So Rawls and other egalitarian theorists have explicated the notion of equality of opportunity in the following way. Equality of opportunity means that the desirable positions and offices in society are open to all, and applications are judged on the basis of merit and not other factors. So this is like an Enlightenment idea. It's actually much older than Rawls, right? It's about careers open to talent. Now, a stronger idea, due to Rawls this time, is fair equality of opportunity. Individuals with the same native talent and ambition should have the same chance of success in competition for desirable positions. That is a more demanding notion of equality of opportunity, because it's not, native talent and merit need not be necessarily the same thing. And how far those are apart from each other is kind of the whole game. Sorry. One way that the ideal of equality of opportunity has been operationalized in machine learning is the idea of predictive invariance. And the idea of predictive invariance is that individuals with the same algorithmic score have the same expected outcome, regardless of race or gender, etc. So here's some examples. Students with the same score on the entrance exam have the same expected GPA. That would be a version of predictive invariance in the educational setting. Or in the risk assessment setting, defendants with the same risk score have the same probability of rearrest, of getting arrested again, if you were to release them. Or applicants, if now we're in the finance settings, applicants with the same credit score have the same probability of repayment, regardless of race, regardless of gender. If you have the same credit score, you have the same probability of repayment. Here's another related notion, but very different one, from psychometrics. So individuals with the same algorithmic score have the same latent merit, regardless of race, gender, etc. So in the educational setting, students with the same score on the entrance exam are in expectation equally gifted, whatever equally gifted means. And here's in the risk assessment setting, defendants with the same risk score pose the same danger to the community. I mean, arrests are only a noisy measure of the danger that you pose to the community. Some people are dangerous and commit crimes and don't get arrested, and some people who don't commit crimes do get arrested. So arrests are just a kind of noisy measurement of danger to the community, and they're not the same thing. Just like your GPA is not a direct measurement of how gifted you are, whatever gifted means. Now, in the financial setting, it's harder to put some distance between merit and expected outcome, because what would it mean for you for two loans to have the same merit Well, it really does mean that they have the same probability of repayment, they have the same expected cash flows, profitability, etc. So there, it's plausible that latent merit really just is the probability of repayment. I mean, of course, if you actually do finance, it's more complicated than the probability of repayment. It's something like how much you expect to make on the loan, it's risk weighted, etc. But we're ignoring that for now. Sorry, there's a cat here. Now, in the machine learning literature on algorithmic fairness, researchers tend to focus on predictive invariance, and measurement invariance, although central to psychometrics, is not usually mentioned. So here is a paper, Risk, Race, and Recidivism in Criminology. So they say, given that the raison d'etre for risk assessment instruments is to predict recidivism, the paramount indicator of test bias is predictive bias. On utilitarian grounds alone, any instrument used to inform sentencing must be shown to predict recidivism with similar accuracy across groups. But the problem is when we're talking about recidivism, what they mean is the probability of getting rearrested, not the probability of committing some heinous crime, right? And getting rearrested is not the same thing as committing a crime. It's just some people are arrested even though they don't commit crimes, and some people commit crimes, but they aren't arrested. So these just aren't the same things. And here is a paper from Michael Kearns and Matthew Joseph. So their analogy is with contextual learning. So in contextual learning, you're faced with a bunch of slot machines, and you have some trade-off between exploring the different slot machines where you want to know how winning each slot machine is, and like going with the slot machines that you know. So in this kind of several two-armed bandit problems, the point is that there's some ideal way of balancing exploring the different slot machines with gathering, like going with slot machines that you know a lot about, right? And whose winningness you've estimated accurately. And so they have this analogy to the contextual learning problem. So our notion of individual fairness is very simple. It states that it's unfair to preferentially choose one individual over another if he or she is not as qualified as the other individual. In contextual learning, the quality of an arm is clear, its expected reward. We view different arms as representing different populations, different ethnic groups, cultures, or other divisions, and we view the context, et cetera, each population. So basically, the idea is the algorithm is said to be discriminatory if it preferentially chooses the low, if it ever, with high probability, chooses the lower quality arm. But what is quality? Quality is just expected reward. And when we're talking about slot machines, the merit of a slot machine, it's very plausible, is just its expected payout. But when we're talking about people, the merit of a person is not, directly speaking, their expected payout, because, well, people's expected outcomes can be poor even though their merit is high, especially if society is unfair, right? That's kind of what we would expect if society is unfair. In a series of papers, Millsap proves that predictive invariance and measurement invariance are typically incompatible. So algorithms satisfying one will typically not satisfy the other. So here's a quick argument for why, if you have predictive invariance, then you must have measurement bias. Now, suppose equal scores on an entrance exam imply equal expected GPA. So we have predictive invariance. In a classless society, if a poor student has the same expected GPA as a rich one, she must be compensating for economic headwinds, like having to work outside of class or do lots of little on-campus jobs. She's compensating for that with superior talents. So equal scores on the entrance exam for students of different classes mean different things about latent giftedness. So if you have predictive invariance, you must have measurement bias, because the same score on the entrance exam does not mean the same latent giftedness, whatever that is. And here in the risk assessment setting, suppose equal risk scores imply equal chance of being rearrested. In a racist society, a Black defendant has a higher chance of being arrested for reasons unrelated to the threat they pose to the community. So equal risk scores, meaning equal chances of getting rearrested, actually mean different things about the danger posed to the community. If we would expect that if a Black defendant has the same probability of being rearrested as a white one, they're actually less dangerous. It's just because the police tend to be in their neighborhood or tend to, be more suspicious of Black people. So predictive invariance and measurement invariance are compatible only if expected outcomes are direct expressions of merit. In other words, only if society is already fair. When are your expected outcomes a kind of unbiased measurement of your latent merit? Well, that's if society is fair already, right? So imposing predictive invariance when society is unfair is not likely to make society more fair, but I would say rather less. Of course, if you really want to develop methods that are measurement invariance, that requires methodology for inferring latent variables reliably. And that's like, one of the hardest things there is to do in methodology. It's like how to infer latent variables. That is a whole difficult subject, but it's not an impossible subject. And our colleagues in psychometrics have been working on it for a long time. And so there has to be something to it, right? And can advances in causal inference help us do these things reliably? I mean, I'm not saying that we should switch to measurement invariance, but if we can develop, if we did have reliable methods for inferring latent merit, and it was possible to make the measurement invariant, I think we should switch. And now the question is, the methodological question is, so the ethics to me is obvious somehow, but the methodology is all very murky and mysterious because I just don't know. Now, maybe some of you do know, but I think this is just a research question for me. Can advances in causal inference help? Can these amazing recent papers, causal discovery with Lingham models under measurement error, structural identifiability results in UAI 2018, can that help us build measurement invariant algorithms and reliably infer latent merit? I think that's the big question for me, anyway. Okay, so on that, I will end. Thank you for being patient.